Good afternoon, everyone. My name is Rohit Upadhyaya, and I'm working with Dr. Abhishek Tiwari at IIT Roper. And first of all, I would like to thank ESIS for the support in this conference to waive off my registration fees. So I will be presenting my work on the topic application of configurational force-based concept of material inhomogeneity to enhance the crack resistance of the material. So first of all, let us look like why do we need material inhomogeneity? So if we need two or three or multiple properties on a single component, then in those cases, we can use the concept of material inhomogeneity by joining two different materials. So here in this case, we can see that two different materials are joined with the help of on this interlayer, and it is good for the cases of uniaxial loading. But for the cases of biaxial loading, this interlayer can cause a problem. Like it can lead to the opening of the interlayer. So in those cases, we can place hole into it. So hole replacing the interlayer in the biaxial loading, it is good to arrest the crack as well as to improve the fracture toughness of the material. So in those biaxial loading applications, we can use hole in place of interlayers or in place of joining two different materials. Now, let us look into some basic concept of the configurational forces, which I will be using here to predict the crack driving force. So the configurational force is a driving force which is responsible for the motion of a defect in a material, and it arises if the total energy of the system varies. So basically the expression of the configurational force arrives from the bulk configurational stress, which is equal to phi I minus Ft into S, where phi is strain energy density, F is deformation gradient, S is first pillar of stress, and I is identity tensor. So here, this is the example of a simple compact tension specimen where the near tip contour and the far field contour is mentioned. And through this configuration force concept, we can find out the value of the near tip contour as well as far field contour, like this one. In this expression, we can see that the bulk configurational force can be expressed as negative of the divergence of the bulk configurational stress, and the J integral for the particular contour, whether the near tip or far field, can be expressed as a vector dot product of the bulk configurational force, like summation of that thing. And from there, we can find out the value of the near tip J integral as well as far field J integral. And after finding out the value of the near tip and far field, we can predict the shielding effect as well as the anti-shielding effect. Suppose the near tip J integral is greater than far field J integral. In those cases, the crack will experience higher crack driving force, leading to the anti-shielding effect. So we will be using this concept in the work. So for that, we have taken several specimen configurations. First one is shown as homogeneous one. Second is the specimen with a hole of a diameter 3 mm. This one is the specimen with a hole of a diameter 2.5 mm. And in here, the three holes are taken. And in this case, the two holes are taken horizontally. Now, first of all, the numerical analysis is done based on the configurational forces. The modeling is done, and the near tip contour, here we can see this one is the near tip contour, which is set as J05 mm, and this one is far field contour. Now, the properties which I have used here for the simulation work is mentioned here. The material is actually SS304, and the tensile properties are evaluated, and these are the value of the Poisson ratio and modulus which I have used in the simulation. And from the simulation, I have found the value of near tip J integral as well as far field J integral, and from that we can predict through some results. As we all have studied earlier in the field of fracture mechanics, like J integral is path independent for the case of homogeneous specimen. So if the J integral is path independent, then J near tip should be equal to J far, then the ratio should be equal to 1. It means that J by J far is equal to 1, meaning that J integral is path independent. But for the specimen with hole onto it, we can see that the J integral is path dependent actually. Now here we can see that the value of J by J far is getting greater than 1. It means that the crack is experiencing higher crack driving force for the case of a specimen with hole in comparison to the homogeneous specimen. Now, let us look for the different cases. Like in this case, the hole diameter is 3 mm. In this case, 3 holes are there of the diameter 2.5 mm. Here in this case, a single hole is there of the diameter 2.5 mm. And here in the last case, 2 holes are present of the diameter 2.6 mm. So here, in this case, we can see that this rectangular bar, the hole of the diameter 3 mm has a higher crack driving force in comparison to the other one, which simply indicates that if we increase the hole diameter for the elastic plastic material, the crack driving force should be higher as compared to the other one. Now, the other result, that is the hole of the diameter 2.6 mm and the holes are placed horizontally, we can see that this cross sign is just below the rectangular sign. That is indicating the result that the hole of the higher diameter has a higher crack driving force compared to the other one. Now, let us take the case where the hole diameter is same, but a single hole is present in this case, and three holes are placed vertically. So we can see that the specimen with a single hole is experiencing higher crack driving force compared to the specimen with three holes. Okay, so this was the analysis where the crack tip was placed before the hole. If the crack tip is placed after the hole, we can see that the crack growth resistance has increased. We can see that the value of J by J far is less than 1. The near tip J integral is lower than the far field J integral. So if the hole diameter is 3 mm, higher the hole diameter, higher will be the crack growth resistance if the crack tip is after the hole boundary. Similarly, for this case where the hole diameter is 2.6 mm, it is little bit on a higher note, and you can see this case here it is getting greater than 1 because there is another hole present after the first hole. So initially there was an impact of the first hole, that's why there was a crack resistance, but after some time as the crack tip changes, the crack driving force got increased because of the second hole present on it. So this was the simulation result based on the configurational forces. Now let us look into the experimental work which I have done to see the impact of the hole on a specimen. Now for the experimental work, I have performed the unloading compliance test, and from the unloading compliance test, I have tried to find out the value of the J integral. And as we know that the J integral can be found out with the help of the elastic component of J integral and plastic component of J integral. And the elastic component of J integral can be found out with the help of this stress intensity factor expression, that is K. Now in this expression, we can see that the function of A by W will change depending on the geometry. Here we are using the different geometry compared to the ASTM standard. We have the geometry which is hole on it. So there is no proper formula for this present in the ASTM standard. So we had to derive the expression of function of A by W with the help of simulation to find out the value of the J integral for the elastic component. Now, this formula is mentioned in the ASTM standard for the homogeneous specimen, but for the specimen with hole on it, we can find out the function of A by W using this thing. We just have to put this denominator to the left hand side, and we can get this expression. And if we put the values of the simulation at the different crack tip, we can get the expression like y equal to mx, and that slope will represent the value of the function of A by W. So in this way, we can find out the function of A by W of our specimen which is diversified. Those formula is not mentioned in the ASTM 1820. So in this way, the function of A by W can be calculated. And further, for the plastic part, we can see some other functions are also there, like eta factor and gamma factor. It will also basically depend on the geometry of the specimen. As I have already said that my specimen has a hole onto it. So we also have to find out the expression of eta factor and gamma factor in order to find out the value of J plastic. So to calculate the value of eta factor, there is a method called as load separation method. The load separation method is said to be as one of the accurate method to find out the value of the eta factor. But it has certain limitations also that I will discuss. So in this load separation method, first of all, the separation parameter can be found out with the help of the ratio of the loads at AI crack length for the reference AJ crack length. So first, initially, this load separation method was given by the Cherubin et al. And he gave that power law of fit is giving the constant value of eta PL for the CT specimen. But if we look into the ASTM standard, the ASTM standard gives the value of varying. ASTM standard value of the eta factor is varying. So we have to modify this. So some modifications are done by the Bain et al. So here in the first case, the power law fit was taken, but in this case, the polynomial fits were taken. So in order to find out the value of eta factor, but this is the result which I have calculated, and I found that this polynomial fit is not true that in every case this polynomial fit will be in good agreement with the ASTM standard. here we can see that this is the ASTM standard line, and no other polynomial fit is in good match with this ASTM standard. So we have to develop some other method which can give the value of the eta factor which is in good agreement with the ASTM standard. Now, let us look into some basic idea of the load separation method. So, as I said, Cherubim and Landes has used the power law method to find out the value of eta factor. But what they have taken the complete range of power law fit. So for that, in my case, what I have done, I have just divided the sections. Like I have divided the crack length part to the 0.5 mm. So let me show you the result. In this result, we can see that for every 0.5 range, I have tried to find out the value of the I have implemented the power law fit in every 0.5 range, and from that thing, I found that this ASTM standard result is in good agreement with the small range load separation method. I have named this method as a small range load separation method, and if it is matching well for the range of A by W greater than 0.5, then we can use the formula which is derived through the simulation for the A by W less than 0.5. So I have done the polynomial fit for that point, and after that I have evaluated the expression of eta factor, and gamma factor is also given by the load separation method. And this is the result of the function of A by W, which I found by the concept which I explained earlier. Here we can see that the ASTM standard function of A by W is in good agreement with the finite element result. That means for the specimen with hole onto it, the function of A by W, we can use this concept to find out the value of function of A by W. So after finding the value of eta factor, gamma factor, and function of A by W, we can implement all these things into the J integral expression. I will just explain this result because of the lack of time. So here we can see that the homogeneous specimen, the value of the J integral got increased, but for the specimen with hole onto it, the J integral got decreased. It means that the energy required to propagate the crack in presence of hole requires lesser energy compared to the homogeneous specimen. This is the first point. Another point is that for the specimen having the hole diameter 3 mm, you can see the decreasing rate is quite higher compared to the other kind of specimen, which means that the specimen with larger hole diameter has a higher affinity to attract the crack in comparison to the other specimen. So I hope I'm on time. So 1 minute. Okay, so experimental result was found to be in good agreement with the simulation results for some cases. I also wanted to explain some more things, but because of the lack of time, I have to finish it well. So the eta factor evaluated using the enhanced load separation method is giving good result compared to the previously derived polynomial fit. And the configurational force result of the J by JFR shows the specimen with larger hole diameter has a higher affinity to attract the crack. And the experimental J delta curve is in good agreement with the simulation result. And the specimen with 2 holes horizontally has a high tendency to attract the crack compared to the specimen with 3 holes. And the specimen with 3 holes vertically will restrict the crack more compared to the specimen with 1 hole of the same diameter. Thank you. So if there are some easy questions, I'm ready to welcome. Thank you.